I'm Ben Sauerwine, and this is a talk I'm giving for the Pittsburgh Biophysical Theory Club on November 10th, 2010, titled Arrhenius Lifetimes of RNA Structures from the Free Energy Landscape. I'll start by giving an example of an RNA where conformation is important for its function. Then I'll explain to you what secondary structure is, and also just what the Arrhenius law is. Next I'll explain some of my methods, including kinetic Monte Carlo, mean and median first passage time, and heuristic methods based on the Arrhenius law. Finally, I'll show you some results and convince you, hopefully, that this works. The creature you see here is the XPT riboswitch. It's a guanine riboswitch active on the XPT gene in Bacillus subtilis. This particular riboswitch is active at the time of transcription. That means that as the RNA is being transcribed from the DNA by RNA polymerase from the 5' to the 3' end, this riboswitch has maybe a couple minutes to perform all of its functions, which are contingent on the particular conformation that this riboswitch takes. In the event that there's guanine in solution, the aptamer structure will be stabilized by the presence of this guanine, as you see in the left-hand picture. When the aptamer is stable and the red anti-terminator is transcribed, the red anti-terminator will not be able to outcompete the aptamer, and that will leave the nucleotides on the terminator hairpin free to bind. When this terminator hairpin is formed, this turns off transcription of the gene. On the other hand, in the event that the same piece of RNA does not find the ligand in solution, as on the right-hand picture, the anti-terminator is able to outcompete the aptamer on the RNA chain. When the anti-terminator forms, even though the terminator structure is more thermodynamically stable, the terminator is not able to outcompete the anti-terminator over the time frame that it has to form in. Because of that, genetic transcription continues past the terminator hairpin and allows the XPT gene to be formed as a messenger RNA. I wanted to take a moment to review secondary structure. Secondary structure concerns itself only with the nucleotide pairings along an RNA chain, and not the shape the RNA chain takes in three-dimensional space or tertiary contacts known as pseudoknots. There are a lot of secondary structures available, even to very short RNA sequences. Here I've listed the 100 most stable secondary structures for a sequence we'll see again later, and this is just 5% of the available structures to this particular sequence. Since we're doing kinetic Monte Carlo, we also have a notion of adjacency that I'll discuss later. And because some of these structures are considered to be reachable in an elementary move from other structures, we also have a notion of a local minimum and a saddle point, which we call a barrier between two structures. The saddle point, as you may know, is the lowest maximum energy we could possibly visit as we travel from one conformation to another conformation. The figure on the right shows a schematic of the local free energy minima, which are starred in red, green, blue, and purple, and the very same sequences are highlighted in the same color on the left-hand side in the list of the 100 most stable conformations available. The whole point of this talk is to convince you that the saddle points alone are not sufficient to tell you about the lifetimes of the metastable states. This is a simplified argument as to why that should be the case. The maximum and minimum energy available to your sequence are proportional to the number of pairs that sequence can possibly make, which is itself proportional to the length of the sequence. So your energy range is growing linearly as your sequence gets longer. However, the number of conformations available to that sequence is related to the product of Catalan numbers, which is the topologies available by virtue of your nucleotide pairings, times the number of ways to distribute the unpaired nucleotides, which is the combination you see there. And this is growing exponentially in the length of the sequence n. Now, however, since we're trying to fit an exponential number of states into a linearly growing space, we know that at some point the density of states must be growing exponentially, especially if we've got a single local minimum. Now, if we take the Boltzmann weight for a particular energy E and multiply that by the entropy at this energy as given by the density of states, we get an order of 1 contribution to the lifetime of the metastable pathways by the higher energy state. The final piece of background I need to give you is the Arrhenius law itself. It's something you've seen in high school, I'm sure, and it's pretty simple to derive from the 3-state system you see here. So in my 3-state system, I'm going to start with a population of particles in the basin or the barrier states, and once they visit my trap state, they're lost to me forever. They've now traversed to something far more stable. So the rate to reach the trap is going to be proportional to how many particles are in my barrier state versus in the basin state. So here I can calculate that in the canonical ensemble, and you see there in equation 5, if the barrier state is relatively high energy compared to the basin state, then the denominator is going to be dominated by the energy of the basin, and I retrieve my Arrhenius law for there in the approximation, where basin energy is much lower than barrier energy. Now I want to move on to my methods. Since all of my methods require a notion of adjacency, I'm going to use the adjacency from my Monte Carlo simulator, which I downloaded from the Vienna RNA package. And here you see an example of what kind of moves are allowed from a particular RNA secondary structure. So you see in my RNA, A may bind with U and C may bind with G, and each structure has a unique little parenthesis diagram that can go with it. This is a property of secondary structure. So my initial state you see there in the center may choose to have one of its pairs change partner, as you see on the left. It may dissolve an existing nucleotide pair there in the center, or it may nucleate a new nucleotide pair, as you see on the right-hand side. And from this, I get a whole bunch of moves and a whole bunch of states adjacent to my original state. Since I'm doing kinetic Monte Carlo, you've probably already figured out where I'm going with this. Now that I've got an adjacency matrix, I need to know my rate to go to each one of my adjacent states. For the purposes of this talk, I'll choose the metropolis dynamics. And this is familiar to many physicists and many simulators. It's given in laborious math there on equation 6, and equation 7 gives you a general picture of what my rate matrix looks like. So along the diagonal, I have the rates to exit this particular state I, and off diagonal I have either 0 if the states are not adjacent, or metropolis rates if my states are adjacent. My Monte Carlo simulator kinfold implements the Gillespie method, or as you may know it, the n-fold way. So if I sit at stem state Si, my probability to go to neighbor state Sj is related to my rate between state I and state j, which I can get from my rate matrix I gave previously. So once I've decided which state I'm going to, then I can figure out how much time I need to take to go to that state by selecting a random variable and using the total flux, or the total rate, to leave the state I started in. The random variable just serves to make sure that my time fits an exponential distribution to leave the state.